Now we have been able to find the basis vectors in the matrix representation. Next thing is, what about the operator itself? Also we have, okay, let me write the two operators. One is a trivial identity. The sum of the projectors should add up to 1. That's the completeness. Nice. And the other is the SZ itself will be h bar over 2 plus. Oh, by the way, this wasn't this wasn't really the purpose. I was planning to come up with the matrix representation of it. What is the matrix representation of it? You just take plus, 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 minus, minus, plus, minus, minus elements, and they form a square 2 by 2 matrix, right? You may say, is it too trivial? Yeah, I'm sorry, I apologize. It's too trivial, but this is the beginning of the class, so let me do it. If you take the plus plus matrix element of this, the second term is obviously giving you 0 using the orthonormality of the bases. The first one gives you, the plus plus is 1, plus plus is 1, so that's 1. This is 0, that's 0. That's 1 again. Let's see why this second one is 1. The first term doesn't contribute. Use the orthonormalization property of the bases. This one gives you minus, 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 minus 1. So matrix representation is this. Is this big deal? Of course not. Well, if you have an identity operator, it's natural in a two-dimensional space that matrix representation should be this. So it took us about a minute. Sorry for that waste of time. So we constructed that unit matrix associated with this unit operator. Okay, so this is the unit operator, and that's its matrix representation in the spaces. Second is, what is the matrix representation of the SZ? Okay, here is the SZ, which I would like to construct. This is the matrix representation, so it should be plus SZ plus plus SZ minus. That's the usual rule, right? We go through our notation. That rows are and columns are there. What was the matrix representation? The operator was written here. This was the operator. So what we do is take the plus, 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 minus, minus, plus, and minus, minus representation of this. Well, let me do one of them, and I invite you just for enjoy fun of it. It's not something big deal. Huh? Let me compute this one. Otherwise, we would be wasting too much time. Huh? I take this operator now, sandwich between h bar over 2 plus plus plus, right? And minus minus. That's essentially what I am doing, correct? Here is the SC operator, and here are the matrix plus plus matrix elements. So it's h bar over 2. Now notice that plus plus gives you 1. That's another plus plus 1. So this is 1. How about the second? Minus plus is 0 because they're orthonormal. So this one is 1 with an h bar over 2. So let me just write the result down. I invite you to verify using this argument. This is the construction, which is important. You know, you have to use the basic algorithm. This is the algorithm how to construct these matrix representations. So it comes out to be 1 and minus 1. You may wonder, why did I get a minus 1 in there? A quick check. This is the thing. This is the element. So I'll use the eraser. You redo it, please. So if I do minus, that will be the minus all the way. The first term is 0, obviously, if nothing, because of both of them. The second one is 1 and 1, but there is a minus in the front. You see? Oh, you say, oh, that's the third Pauli matrix. Of course. That's how you construct it. You're using the basic axioms of the quantum theory. It's not out of the hat. There's a logic behind that. It is the matrix representation in what basis? In the eigenvector basis of the SZ itself. Sometimes it's overlooked. There's a well-defined basis, the eigenvectors of the SZ, and it's natural that, as I will elaborate further, it's natural that it's diagonal, it's in own eigenvector basis. That's the general theorem. But Sx and Sy will not come out to be diagonal. They will be off-diagonal for very good reasons. But if you were using the basis, which is the eigenvectors of the Sx, for instance, you may have a different set of representation. They are unitarily equivalent, but that's a different representation. So pay attention to the fact that when the usual representation of the Pauli matrices are matrices in the eigenvector basis of the SZ operator itself. One more thing before jumping into measurement business. Here we can think of the other operators. Still we are in the illustration section. Consider the following operator: plus, minus. That's one likely operator that we can think of. Let me put an H bar in it and let's define this to be S plus. I'm not just defining it. And let me define another operator. Outer products of the cats are operators. That's another operator, plus. Let me define it as minus. You may wish now to find the matrix representations of these new operators. Let's do it. What are the matrix representations of them? Again, you go to the plus. Here, this is the table that you have to reconsider and replace these SCs in here with the S pluses and S minuses. Then obviously, the only term, when it is S plus, the only term which will be non-vanishing is this term in here. All the other terms should vanish, right? Because it's sandwiched between minus and minus and plus, minus and plus, and plus and plus. So the only term will be this. The matrix representation will be H bar 0, 1, 0, 0. And similarly, the matrix representation of this will be the only term which is non-vanishing is this bottom diagonal one. How to make use of this, we will see it eventually. Okay. Now we move into the measurement business again. Okay. We have been discussing the measurement from the beginning, right? Because measurement is the only way that we can collect information in physics. Whether it's classical or quantum, doesn't matter. You just carry out measurements. If it is an experiment, you can carry out the measurement directly under control in the laboratory. If it is an observation for astronomical purposes, you still carry out measurements, but it is not direct measurements at a distance. But anyway, you always carry out measurements. But we have also seen that because we are in the micro world, whenever you measure, you disturb. You measure, you disturb the system, and we have discussed the Gedanken experiment of the Heisenberg, and we can quote Mr. Dirac. I guess he was the first to use this eventually, which is picked up and used further by the Heisenberg. The collapse or jump, the concept of state collapse or state jump. It is the following. When you carry out a measurement of a given observable, denoted by any arbitrary A, it could be position or momentum, or, I say or, not n, because now we know that you cannot really, I will discuss the simultaneous measurability in a few moments, but you think of individual measurements. For example, you think of measuring Sx, x component of the spin, or y component of the spin, or the z component. But whenever you measure a system which is known to be in an arbitrary quantum state, you collapse that quantum state into the associated eigenstate of the measured quantity far out. It's a very profound statement, isn't it? There are so many things, so many elements entering into that statement. I guess that particular statement is due to Mr. Dirac. You carry out position. Originally, the state is arbitrary. It could, in principle, be thought of being superposed of any set of eigenstates before you interfered. Whatever the physically relevant if it is spin system, two-dimensional, you better say easy, right? You can say it is either spin x or spin y or spin z, any direction. So they could have been an arbitrary state before entering into the measurement devices. It could be superposed, it could be thought of as a superposition of in terms of any basis vectors. But when you let it go through a z type of Stengerlach, obviously at the back of your mind you have the idea of measuring the z component. It rearranges itself, finds itself in the z eigenstate superpositions and collapses into either plus or minus. Whatever result comes out, there are likely equal probability of any of the results coming out. 50%. Up state may come out, 50% minus state. The down state may come up, but whatever result comes out, the state collapses into the eigenstate of that associated eigenvalue. Isn't that amazing? That's really at the heart of the measurement theory. So this subject is measurement again. Well, we will be talking about measurement so much, we started by talking about measurement at the beginning and we keep talking about it. So before the measurement, our state was in an arbitrary ket. We are carrying out a measurement here of a given thing, like z component of the spin, or position, x component of position. Well, if you are entering into the measurement device in here. You measure it with at the end of the measurement with the result AI. Here is the measurement phase. And you end up yourself being in the state AI. Measurement intervenes and changes the state, causing it to collapse into that. That's, as I said, it summarizes everything, that beautiful picture. Is there an exception to this? Yes. If it is exception, if it is already known to be in the AI state, that's the before state, that's the during, that's after. Let's put it during the measurement. That's what you are doing the measurement. This is the after. So if it is already before AI, we have seen in the sequential Stengerlach experiment thing, I will plot a picture for this. You go through with the same statements. You are measuring the A variable. Of course, you'll get the result AI. The state will continue to be in the AI. So that's the exception. This was arbitrary, the initially known to be in the AI eigenstate. So what is the probability of finding this or equivalent thing? What is the probability of collapsing into this? They're differently expressed, but boiling down to the same thing, right? Because you know that finding this is a result of that it's being collapsed into that. So probability is probability of finding AI or collapsing into A is equal to that. Notice that this statement is a postulate of the quantum theory, or a different version of the so-called Born's rule. In principle, you cannot really drive this. Although there are some recent developments nowadays picking up momentum, elevating this research, and they are trying to find alternatives to the Copenhagen interpretation. One likely alternative is the so-called many worlds or the multi-universe models. And there are claims that in those new versions, one can drive this rule, so-called Born rule. Otherwise, in the Copenhagen interpretation, it's built in as a postulate, not something that you can drive. But as I said, these new alternatives claim that they have a way of deriving that result. Okay. By the way, I have written recently a popular article on it in one of the Turkish journals, Bilim Ütopya. If you are interested, you can take a look at it, okay? So here there's a nice half a page discussion in here. If you're interested, go ahead and read it, please. Well, obviously here there are certain things which I have to further elaborate. Probability for anything. I'm making some reference to the basic axioms of the probability in here when we are saying probability. Probabilities have the two features. They must be non-negative. Although in the recent past there have been some research to accommodate the negative probabilities. In the conventional quantum theory, based on Copenhagen interpretation, we are using the standard axioms of the probability theory. Probabilities are non-negative. That's the first axiom. Second axiom is that the sum over all options, all possible cases, should add up to 1. So when you say probability, these two points are to be kept under consideration. Obviously, that probability is consistent with that basic axiom. It's being the mod square of a complex number, obviously it's non-negative. And if you sum, oh, by the way, let's check that. That's obviously, well, positive. Only in the exception trivial case, it may be equal to 0. It's really non-negative. The sum, is this 1? Well, that's really 1, obviously, which can be, I can construct it to be 1, but I can even demonstrate that it is 1 in a trivial manner. How do I do that? You write this as AI, alpha AI complex conjugate. I skipped one step for obvious reasons. AI alpha complex, so it is this. Sum over I. Put that summation in here and use the completeness argument. That's identity. That's 1. if you are using normalized state vectors, which you have to, then the general state vector should be normalized. And so this probability of finding any one of those results, right? Because you have options of finding various values of the eigenvalues as a result of this measurement. So the probabilities of finding each of them is given by these single entities. And then you sum them over all the options. You use the completeness by writing this complex conjugate times itself. Use the completeness, you get to 1. Anyway, as I said, all these things are built into the system, so it's not surprising. It's a verification of these statements. Now here I have to introduce the concept of expectation value, although I have been talking about it in a hideous manner, because as I said, when you're really constructing the mathematical formalism of quantum theory, you should borrow either from the future or because we are not from the past. We are not really starting from the scratch at all. So I remember talking about this expectation value thing, but here I will define it with mathematically now. Expectation value of an operator. Let me write it, and I will move away from the scenery so that it can be seen. Expectation value of operator A, symbolically, shorthand is this. But this shorthand doesn't mean much. Because when you are talking about an operator, an expectation value, the state in which you take the expectation value should really also be denoted or depicted explicitly. Well, let me use the book's notation. My favorite before was psi, but the book uses alpha, so I have to go back to the alpha. So it is the state alpha, and that's the expectation value of the A in that state. So if you are using a shorthand like this, it is suggestive that you put that label in which state you are taking the expectation value. It's in this state. Now there is a sort of inner feeling that it must be related somehow to the average measured value. Even the word that you're using to define it implies that. Expectation value, is it really the same as average measured value? Well, of course, the answer will be yes. Let's illustrate this. It's not too difficult to illustrate it. It's indeed the average measured value. For that, of course, I have to, in order to establish contact with the measurement, I have to introduce I have to refer to the possible values that you can find as a result of measurement. We know that the possible values are the eigenvalues of it with certain weights. If it is a direct eigenstate, you'll get the eigenvalues directly. If it is not, you'll get with the weights, the particular values. The weights are there. But anyway, so let me insert now the alpha A alpha, that's the expectation value I am computing. So what do? Insert identities in here. And the identities are in terms of the eigenvectors of that measured operator itself. If you are measuring A, if you are using a different basis like B, whose kinship to the A you don't know, that's a totally irrelevant thing. I don't call it right or wrong, irrelevant. It doesn't help you in understanding the real dynamics. So what you do is you use that particular eigenvector system here, and also another identity which you have to insert here, AJ and AJ, using different set of indices because there are two different summations involved. So what is this now? Sum over I and J, alpha AI, AI, A, AJ, AJ, alpha. This is the eigenvector of it, gives you the AJ, so it is a diagonal matrix as we have discussed before. This is AJ times the delta IJ. You carry out one of the summations. I'm repeating myself, I know, but I'm doing it on purpose. So what do you get then? Alpha, AI, AI, alpha, or some more AI, AI, alpha squared. So what is this? This is what I denoted as, put the label correctly, alpha. The expectation value of the A operator in the state alpha is the sum of measured values For instance, for a spin 1/2 system, there are two possible measured values, right? H bar over 2 and minus H bar over 2. And those. So what are those? Probability of obtaining AI. This is, if you remember the usual mathematics of statistics or probability theory, that is nothing but the average measured value, right? You take the values of all the values in the spectrum, multiply with the weight, associated weight, that's probability of finding each of them, and add over all of it, that's average measured value, which is we call in mathematics, in the mathematics of quantum theory, we call it the expectation value. So these two terminologies may be used, if you are careful enough, interchangeably, okay? Now we move into a specific type of measurement, which is called selective measurement or filtration. We have seen it before for the simple case of spin 1/2 in the sequential Stangerla system. Selective measurement or filtration is, for example, in the case of spin 1/2, say Z type of Stangerla, you let a beam arbitrarily polarized initially, totally arbitrarily, goes through the Stangerla the gadget, splits into two. Half of the beams are spin aligned, parallel to the magnetic field. Half of it, 50% of it, anti-aligned. So then we blocked, remember, in the sequential system, we blocked the lower component. Then whatever comes out of the Z type of Stangerla, we blocked the second, closed the second port, blocked it, and we let the only up polarized one to go into a second one. Well, that's really a filtration or selective type of measurement. You block a certain part of it, except one option, one possible result you let go, and all the other are filtered out or selected, rejected. Okay, so how do you really, let me schematically show it on the board. What is a typical selective gadget? What we call it, say A measurement. When you are talking about measurement, you have to indicate which dynamical variable you are measuring, of course. There are several results, of course. If you block everything except one of them, which you denote as AI, this I is a specific one. In principle, I runs from 1 to n, because if it is spin 1/2, there are two possible values, up or down. So this may be the plus. And here there will be only another option, minus. But this is the simplest case, of course. So you may have more complicated quantum systems. If it is spin 1, there will be 3 polarizations, plus 1, 0, and minus polarizations. And you may block the lower 2. If you read the Feynman's book, that beautiful book, volume 3 of lectures on physics, all his Stengler type of arguments are based on spin 1. And these gentlemen go to spin 1/2 easier. So Feynman considers 3-state problem mostly. But anyway, it may be, there are so many of it, you block them all, you let only AI go through. Okay. So what is this measurement? How do I represent this mathematically? Mathematically, it can be represented, if this is the initial state, which is arbitrary, there is no measurement is done, so it can have any value, and it can be expressed in terms of any basis, really. When you think of making a measurement on the A, it rearranges itself, it expresses itself as a superposition of the eigenstates of the A operator, and then all the possible results come out. You block everything but catch a specific one. So it means that I am really doing this operation by doing a measurement, this selective or filtration. What is the lambda I? This is the projector AI. I am acting on state. That's the mathematical way of saying that this selective measurement is carried out. You act on it like that, so you get what? AI alpha. Indeed, that's the only state which is selected and being let through. All the rest are blocked. And that's the weight which comes out. Now let me turn my attention to spin 1/2 system once again. Well, spin 1/2 system is so educative. You can really think that most of the quantum mechanical formalism can be built on it. When you talk about in terms of these abstract things, well, it's nice, it's understandable. Now, I guess probably I have repeated myself so much that you now all understand what we are talking about when we say measurement. But it would be nice to illustrate it again on this spin 1/2 system. Okay, so let's pick it up again, illustration. Spin 1/2 system again. Let's pick it up. Well, let me summarize what we have achieved till now before considering the sequential argument once more. We have learned that when you have spin 1/2 system, Stengler experiment is telling us that there are the SZ, its eigenstates are plus and minus these states with the possible values of h bar over 2 and minus h bar over 2. And it has a nice representation itself in the spaces, which is h bar over 2 plus minus. So I know what that expression is in the spaces, and they are orthonormal and complete, so therefore it is given to me. But the point is, if I really pick up this this spin 1/2 system, I aim to achieve the following. If I now put together the results of the sequential results, experimental results, sequential Stengler experiments, being sequential is important, you know. Remember, it taught us a lot concerning the intervening nature of a measurement each time and losing all the previous information in that simple system. So experimental results of sequential Stengerla system plus the postulates that we have formulated till now, postulates of quantum mechanics, will enable us, in addition to these initial information, we have gathered this information quickly and immediately at the first step, and it will give us the information about the Sx and Sy operators. Furthermore, it's the eigenvectors of the Sx as well as the eigenvectors of the Sy. So it's not a modest thing of having an information only on the Z component of the spin or its eigenstates. We will have a complete information about everything now concerning the spin 1/2 system. Well, then we'll say we have a complete quantum theory. If you have full control on the Sx, Sy, Sc together with their eigenvectors and all the features being normalized and completeness, then I say we have a complete framework. How do we do that? Let's have an attempt. This is the aim. The lower bottom is aim. This portion is in inputs that we have already gathered. And let's see whether we can have the second part of it. Now consider, as a starting point, we have, say, let's start an unpolarized one, X type of Stengerla, become with the plus X. And suppose this portion be blocked. This is arbitrary, alpha. When I denote alpha, it means it could be anything. In principle, two components with arbitrary C1 and C2, their mod squares add up to 1, but that's all. Then we go through Stengerla Z. The experiment is telling us that we have equal intensity, Z up polarized and Z down polarized, although input is up X polarized only. Equal intensities. That's the experimental result. What is the probability of getting this out of that? This is an arbitrary, for this system, this is an arbitrary input. And it's like any vector. You can express it in terms of those bases, right? Let me repeat those arguments. You may have plus X is equal to C1 plus Z plus C2 minus Z. C1 mod squared is the probability of getting the plus Z out of this. And C2 is the probability density of getting the minus Z polarized out of the initial beam, which is X. The initial one is an arbitrary input as far as this one is concerned. It could be anything, but I take it to be just plus X. But result is, what's the probability? That probability is the mod square of this. And the probability of the second one is the mod square of that. That is the probability of finding an up polarized beam out coming. That is the probability of finding a down polarized Z in the Z direction. Beam output. The experiment is telling us that they are 50%. 50% is 1/2. So this one is what? Well, this one is, well, the mode of it at least. This is too pedantic, you may think. It is not. If I look at the absolute value of it, it is 1 over the square root of 2. The absolute value of this is also 1 over the square root of 2. What about the C1 and C2 fully? If you allow me, I will use eraser. You use a new line, please. Alpha 1. Well, these are complex numbers. It will have a magnitude and a phase part, right? Any complex number can be represented in terms of 2 real numbers. You use Cartesian language, write it as real x, real plus the I times imaginary, or you use this polar representation. Here are the real parts, here are the phases. So therefore, this plus x can be written as e to the I alpha 1 divided by square root of 2 plus z plus e to the I alpha 2 divided by the square root of 2 minus z. Or e to the I alpha 1 divided by 2 plus z plus e to the I alpha 2 minus alpha 1 times minus z. I'm trying to construct the plus x eigenstate in terms of the default basis vectors, which are the eigenvectors of the z operator. Notice that this is an overall phase. But there are combinations in here, and there is a relative phase between the plus and minus. Obviously, that should have a physically relevant role to play. But the overall phases do not play an important role. No role at all, except in the discrete symmetries, which we are not going to discuss in this lecture. Because expectation values are the ones corresponding to laboratory measurements. Expectation values involve a bra and a cat. In between, you put the operator in question. So a bra and a cat, which one of us have an overall phase e to the I alpha. The bra has e to the minus I alpha. Correspondence between the bra and cat space. So overall phases are not important. So we set this equal to 1 or this phase equal to 0. The phase I set equal to 0. Set equal to 0. So the first coefficient is 1 over square root of 2 only, but this thing is going to stay in here. Let me use a shorthand. You call it the delta 1, this phase. Okay. So here I found what plus x is. I invite you to repeat the same and find the minus x. You just repeat the same procedure. This time block the plus, let the minus go through. Again, you will have, as there is no difference between the upper and lower, the same argument applies, and you'll get a 50% z up aligned, the 50% z down aligned beam, outcoming beams, out of an minus x input. Therefore, I can write plus x is equal to 1 over square root of 2 plus z plus e to the I delta 1 minus z. Similarly, you will get a minus x. Let me write it, and a little more comment may be necessary. You may wonder what happened that I get a minus sign in here. In terms of the z bases, I constructed the plus x first and the minus x next. Well, you pay attention to the following. The presence of phase is something, which is to stay there. This state and that state, these, both of them are eigenstates of Sx. Sx is a Hermitian operator, and eigenvectors of Hermitian operators corresponding to different eigenvalues are orthogonal. And all the components of the S, whether it's Z or X or Y, along any given direction, because the direction doesn't have any meaning. External B defines you a direction. You call it X or Y or Z, that is up to you. So for these also you have eigenvalues plus and minus a half times H bar. But anyway, orthogonality is the important thing. So you can construct this state to be a normalized state orthogonal to the original one. How do you impose that? Okay, a sketch, quick sketch. I don't want to go through it in too much detail. You write it as such. I use different name D1 and D2 not to confuse with the original C1, C2 I used. These are coefficients, complex coefficients, with the mod squares adding up to 1, obviously, because this is a unit, basis vector, meaning that it must be orthogonal, and it must be orthonormal. Normalized, it must be orthogonal to the original one. That is, should be 0. How do you take this one? The inner product of this new state and that state, it gives you 1 over square root of 2. That's the overall. 1, and plus gives you d1, and this is coming from the left, so e to the minus I delta 1, so d2 e to the minus I delta 1 is equal to 0, right? So this tells you that d2 is minus d1 e to the I delta 1. Then you substitute this into that and determine the coefficients, you get this. Pay attention to this minus sign. That's the trace of the minus sign. But the same phase survives. That's nice. Phase surviving is something, relative phases you're not free to touch. You should let them go through. Well, besides they are so profound, that's a demonstration of the fact that, remember, originally we said the state vectors are vectors of a complex Hilbert space. There is ket space and bra space, the dual space. The complexity reflected by the fact that the inner product that you associate the ket and bra space to a complex number. Well, already in this simple example, there's a strong hint that state vectors should be complex if that delta 1 survives. Or similarly for the SY components. We'll see. So we are talking about complex space. We could repeat the same line of reasoning in the following manner. When we let this plus x coming out, instead of putting here a z type of Stengerla, I can put a y type of Stengerla. All these directions are equivalent. There is no difference as far as we are concerned. Whatever you do in one direction, you are free to repeat in any direction you like. So let me quickly plot this new picture so that we can repeat the same analysis that we have done for this sequential system. I will have the x type here and here y type, the new one. Okay, here. I blocked. Okay, let me plot this and I will give a break and we'll continue after the break, okay? Now I'm having a Y type of Stengerla device and we have 50% of the beam coming out with aligned in the positive Y direction and 50% comes aligned in the negative direction. So with their equal intensities. Okay, we'll continue analyzing this after the break.